Pressure remains the ultimate challenge. Standard electronics fail beyond 4,500 meters unless specially protected. Novel cameras resist 11,000 meter pressures by replacing air with fluorocarbon fluid. Solid-state batteries now function at 10,000 meters without protective cases, a critical advancement. Sampling fragile life requires finesse. UR-Ice pressure equalized trawl maintains native pressure during collection, while Jamstack suction sampler gently captures jellyfish that previously turned to mush. A 2023 Nature study proved Hadal snailfish have higher metabolism under pressure than at surface conditions. Communication lags at extreme depths. Fiber optics allow real-time control to 6,000 meters. Beyond that, autonomy takes over. China's Aishing 6,000 transmits just 16 kilobits per second at 10,000 meters, with 7-second latency requiring AI-assisted navigation. Materials push boundaries. The DSV limiting factor's 90 millimeters titanium hull withstands Hadal zone pressures through precise curvature. A 2023 silicon nitride sphere prototype resisted implosion at 12,000 meter equivalent pressures, though costs remain prohibitive at $20 million per hull. Hybrid systems blend capabilities. WHOI's Nereid under ice switches between tethered and autonomous modes. It's 8 kilometers fiber spooling out like a fishing line, before retracting for independent surveys of methane seeps. Navigation achieves new precision. Sydney Sirius AUV maps seafloor features within 10 centimeters at 5,000 meters, aided by quantum gyroscopes that reduce drift to under 1 meter per hour, critical for uncharted trenches. Human-robot teamwork excels. OceanX Ariane's VR-controlled arms collected pristine coral from 1,200 meters, where previous ROVs crushed samples. Operators feel resistance through force feedback, preventing damage to delicate specimens. Costs remain steep at $50,000 daily for ROV operations. New Orpheus-class drones slash expenses by 90%, using off-the-shelf parts to cut unit costs from $5 million to $250,000. Energy limits persist. While most ROVs rely on surface power, China's Haijiao ran 12 hours at 10,000 meters on internal batteries. MIT SoFi robotic fish draws power from seawater like living marine organisms. The future lies in endurance. Wave gliders harness solar and wave power, while planned Argo seafloor charging stations could sustain drone swarms indefinitely, transforming brief expeditions into continuous observation. Even with these advances, the deep remains largely unexplored. The deep ocean's carbon capture secret. The deep ocean holds an estimated 38,000 gigatons of carbon, equivalent to absorbing humanity's current emissions for over 3,000 years. This massive storage occurs through two key mechanisms: physical processes that trap carbon in deep currents, and biological processes that bury it in sediments. Cold, dense polar water absorbs atmospheric CO2 before sinking, initiating global circulation patterns that can lock away carbon for millennia. The Atlantic meridional overturning circulation alone transports 1.5 petagrams of carbon annually into the abyss. Meanwhile, marine snow, a steady shower of dead plankton, fecal matter, and organic debris, rains downward at 1 to 200 meters per day. These tiny particles, some no larger than a grain of sand, carry 5 to 12 gigatons of carbon yearly to the depths, matching our annual CO2 output. Unlike surface carbon that quickly recycles, much becomes sequestered in oxygen-starved sediments, where decomposition slows to a crawl. The efficiency of this biological pump depends on microscopic actors. Diatoms, silica-shelled algae that bloom explosively, create dense marine snow that sinks fast, accounting for 40% of ocean carbon export despite covering less than 1% of surface area. Zooplankton play dual roles. Species that pack waste into tight fecal pellets accelerate carbon transfer, while those that shred particles slow it down. Currents then redistribute this organic snowfall, with about 1% eventually reaching the seafloor. Deep-sea currents act as carbon conveyor belts. Antarctic bottom water formation creates icy rivers along continental slopes. distributing carbon globally over centuries. The Denmark Strait overflow alone buries 300 million tons annually in North Atlantic sediments. Similar processes near Greenland and the Weddell Sea pull carbon downward as part of Earth's thermohaline circulation. Sediment cores reveal the staggering timescales involved. Layers in the Pacific's Clarion-Clipperton Zone accumulate at just 0.5 millimeters per millennium, yet form deposits 500 meters thick, archives of carbon locked away for millions of years. Anaerobic bacteria here metabolize so slowly that some communities show activity dating back 86 million years. Unexpected contributors like cold water corals enhance storage. Their intricate skeletons trap organic particles, boosting local sedimentation rates 15-fold. A single Lophelia pertusa reef, smaller than Central Park, captures 800 tons of carbon yearly. Hydrothermal vents add another twist. Chemosynthetic microbes build entire food webs without sunlight, fixing 0.02 gigatons of carbon annually into vent structures like the 120,000-year-old Lost City chimneys. Human activities now disrupt these ancient systems. Warming waters may weaken carbon-capturing currents by 30% this century. Acidification dissolves pteropod shells 14% faster at depth, while deep-sea trawling stirs up sediments, potentially releasing stored carbon. Even the mesopelagic zone's daily migration of fish, which shuttles carbon downward, remains understudied. Recent sonar scans suggest their biomass could be 10 times previous estimates, implying far greater carbon transport. New technologies are revealing hidden dynamics. Argo floats track carbon particles to 2,000 meters, while NASA's upcoming SWAT satellite will map upwelling zones. Yet mysteries remain, like the 2021 discovery of gelatinous snow from larvacean mucus houses, a fast-sinking carbon pathway previously unaccounted for. The system has limits. Warmer water holds less CO2, and microbial respiration speeds up by 10% per 1 degree Celsius increase, potentially turning sinks into sources. Models suggest storage capacity could decline 20 to 50% by 2200 if emissions continue. As the GeoTraces program tracks isotopes across basins, one truth becomes clear: this immense but fragile carbon bank, developed over eons, is changing faster than we can measure it.